Hi class, welcome to the video version of the lab manual for the 215312 Refrigeration and Air Conditioning Laboratory Test. In this video, we'll go through the learning objectives of this particular lab. We'll also look at the background of vapor compression refrigeration system. Um, we'll also discuss the lab test setup, various components and its purposes, the test procedure itself, including what data to collect, how many tests to run, and then the post-test activities, which will include the detailed data analysis. The learning objectives for this lab are the following. Primarily understanding the major components of the vapor compression system and their functions. Understanding the thermodynamic states of the refrigerant at key state points on the cycle. The ability to correctly operate and read the volume flow rotometers, pressure gauges for the refrigerant, and temperature sensors for both the water and the refrigerant used in the experiments. The ability to measure cooling water and refrigerant side parameters and convert the volumetric flow rates into mass flow rates using their thermodynamic properties like density. Use refrigerant property tables and/or CoolProp software to determine the relevant thermodynamic properties, including enthalpy, entropy, saturation conditions, density, and specific heats of the refrigerant used. In this case, the refrigerant used is R134A. Calculate the heat transfer rate at the two heat exchangers, the evaporator and the condenser, on the water side using the water side temperature measurements and the flow rate measurements. Now do the same thing on the refrigerant side for both the heat exchangers using the refrigerant flow rate measurements and the thermodynamic property measurements done at the inlet and outlet of both those heat exchangers. Compute multiple types of efficiency parameters defined here as coefficient of performance for the overall system, including isentropic, actual, overall, and system COP. We'll define all of them in detail later on. Evaluate the compressor performance alone by calculating the compressor isentropic efficiency and overall wire to refrigerant efficiency. And then identify and explain the sources of all the errors present in the experiment. Now, just to give you a short context or background for this lab, let's look at the common refrigeration technologies that are out there and their typical applications. So refrigeration is basically removal of heat from a system, substance, or a space uh, using a device or a methodology to drop the temperatures below the surrounding temperatures, right? So if you consider that as the definition, there are several different types of devices that do that. Um, a lot of them you can find in your house for domestic application, like household refrigerators, um, beverage coolers, ice makers, and then there are commercial ones. Then you have air conditioning for cooling spaces, um, for buildings, aircrafts, vehicles. So if you look at majority of these applications, you'll see that there are several different technologies, but the most common, I would say about 90% of the time, the technology that's used for cooling is the vapor compression system. The applications um, of other technology are minuscule compared to how much vapor compression systems are out there. And one of the main reasons for that is the efficiency, which is defined as the coefficient of performance, right? So higher the COP number, the better efficient the system is. So if you look at the vapor compression system, even though it is a little bit complex than some of these systems, it is um, it's worth value for the money because of the efficiency. And especially when you consider things like refrigerators run throughout the year for many years, the reliability and the efficiency of the vapor compression system is unmatched by any of the other systems. The refrigeration technology that you will study in this lab is also a vapor compression system. Okay, all right, and it's applicable to both um, domestic refrigerators and air conditioners. It's also applicable to heat pumps that are used for heating. All of them fall under the vapor compression cycle. Now, here, if you don't know what efficiency is, it's defined here. It's output over input. The input is typically the electrical power that you supply to the system, and the output is the amount of cooling that the system provides, um, which is basically the heat removed by the refrigeration system from the space or the substance that you want to remove the heat from. Now let's do a quick refresher on the basics of the vapor compression cycle. We'll start with an ideal vapor compression cycle, and we'll analyze it using a pH diagram. As you know, you could do this thermodynamic cycle analysis either with a TS diagram like this or a pH diagram. But if you look at uh, the four processes involved in a vapor compression cycle, two of them are constant pressure processes. Okay, this one and this one. One happens in condenser pressure, one happens at the evaporator pressure. The third process is a constant enthalpy process. Okay, it's a vertical line. So three of the four processes are either a constant P or a constant H. So it's easier to analyze such a cycle on a pH diagram. You could also do the analysis on a TS diagram, but for the majority of the time, VCR cycles are analyzed using pH diagrams. So let's start with the components first. We have a compressor, which is at the heart of the cycle, which moves the refrigerant and uh, is the main reason for the cycle to continue. Then we have a condenser, which rejects heat from the refrigerant. We have an expansion device, which does the opposite of compression, where it drops the pressure back to the original pressure of the refrigerant. And then we have an evaporator, which actually cools the space or the substance which we are trying to cool. Let's start with the compressor inlet. So compressor inlet is point 1, which is here in the cycle. And from 1 to 2, what happens? We are definitely seeing an increase in pressure from the evaporator pressure to the condenser pressure. And then we also seeing an increase in enthalpy from H1 to H2, right? So the compressor is basically working on the fluid. It's adding pressure and enthalpy to the fluid. Now, how is it doing that? It's doing that on an isentropic manner. In other words, it's an isentropic compression process. What does that mean? That means there is no losses. There is no heat losses. There's no heat transfer. It's adiabatic. There is no friction, which will lose some of the work as heat. And the work is done in a really slow manner such that there is no non-equilibriums inside the fluid. In other words, the pressure is constant everywhere. If you think about inside the cylinder where the compression is happening, the pressure and temperature inside that cylinder is constant everywhere. It's uniform. So that will only happen if the compression is happening really slow. So assuming such ideal compressor is available to you, then you will be operating along this line, isentropic line here. So this is an isentropic line, right? So S1 is same as S2. So isentropic compression from 1 to 2. And when you finish the compression, you exit at the highest temperature possible in the system. Okay. Now that compression is done, you have to cool that fluid in the condenser. So initially, you're cooling and the temperature drops. And when you hit this point, This is the saturation curve, or you can call it the vapor dome, right? So inside it is two-phase, and outside on the right side is vapor, and on the left side is liquid, right? So the vapor is superheated vapor, the liquid is subcooled liquid. That's another way to call it. And inside they have both liquid and vapor. So after it reaches the point 2 prime, if you cool further in the condenser, right? First of all, you're reducing temperature because you're cooling the condenser, and you can cool it using water or air or by direct contact with a colder substance, right? So in our lab, we are using water-cooled condenser. Now, when you cool the condenser, its enthalpy keeps dropping from H2 all the way to H2 prime and then all the way down to H3, right? Um, why does that happen? Because you're removing heat. And the way the condenser is designed, the tubes and everything, it's to ensure that there is no pressure drop, right? So there is no pressure drop, it's happening at condenser pressure, but there is a temperature drop up to here. After this, the temperature is constant, and you can call that temperature as condenser temperature. Okay, and it stops at point 3. Point 3 is also on the dome where all the vapor in the condenser has turned into liquid. Okay, and if you cool it any further, it will be subcooled liquid. So there is only liquid at this point when you reach this dome. Okay, when you reach the this point on the dome, and then it goes through an expansion device, 3 to 4. And when it expands, now you have both liquid and gas again. So you're inside the dome. And then you reach the inside inlet of the evaporator, which is point 4. So between 3 and 4, there is no heat addition, there is no work done. Okay, so the enthalpy is the same. It's the same as the throttling process we discussed in the refrigeration class. So 3 to 4, the throttling process means isenthalpic. So H3 is H4, it comes down vertically. From H4 to H1, the enthalpy increases. Why? Because we are removing heat or we are adding heat to the evaporator. Evaporator is removing heat from the substance or the room or a space which it's trying to cool. So you're adding heat again at constant pressure, which we'll call evaporator pressure, PE. So that pressure remains constant throughout, and the temperature remains constant from inside the dome. Okay, and the liquid in vapor mixture becomes less in liquid and becomes more in vapor. And finally, when we reach 1, it's all vapor. And vapor goes into the compressor, right? Isentropic compressor. There's no liquid going to the compressor. So as the vapor reaches 1, we finish the end of the evaporator, and we can say it's going into the inside of the compressor. And the cycle repeats. Okay. Now, how do we calculate the efficiency of the cycle? In this case, the output for the efficiency is the refrigeration capacity. It's the enthalpy difference between 1 and 4. Um, so in this case, refrigeration capacity, I think I wrote it wrong. It should be H1 minus H4, joules per kilogram. Okay, the units here are joules per kilogram, and you could say pressure is in pascals. So the evaporator heat transfer is H1 minus H4 joules per kilogram. Now, if you want to convert that into power, you multiply with the refrigerant mass flow rate, which is in kilogram per second. So the heat transferred in the evaporator side, which is the lower temperature, Q dot L, is this value in watts. Same thing in the condenser, you could easily use the enthalpies at 2 and 3. You can easily see that it'll be a quantity like that. And H4 and H3 are same. We already know that. And the work done by the compressor is basically you look at the enthalpy at 2 and 1 and multiply that with the mass flow rate again. The efficiency would be work done by the compressor by the ratio of the work done by the compressor and the ratio of the work done by the compressor and the cooling capacity, which is the amount of heat removed at the evaporator, which is QL. So this enthalpy ratio is the efficiency of the thermodynamic cycle. Okay, so this is the, if you have a VCRS cycle, the best efficiency it can get is basically based on this ideal condition. And the things that make it ideal are, one is the isentropic compression process, 1 to 2. 2, the exit of the condenser is exactly on the saturation line. 3, the exit of the evaporator is exactly on the saturation line. So if these three conditions are primarily met, then it's an ideal VCRS. You could also say that there should not be any pressure drop here and here. The pressure should be constant. So when you have a cycle like that, it's an ideal VCRS, and this is the COP calculation you have to do. And we have discussed this where the evap temperature is same in 1, 4, and the condenser temperature is same from 3 to 2 prime. Okay. All right. And the evap pressure is the saturation pressure corresponding to evap temperature TE, and the evaporator condenser pressure is the saturation pressure corresponding to condenser temperature TC. All right. Now, the actual cycle is going to be different from the ideal cycle. So what are the three main differences? Subcooling, superheating, and non-isentropic compression. So like I said, the three things that made it ideal, if they are different, they become actual. So the biggest difference is the compression process. 1 prime to 2 prime was the isentropic compression, but in reality, it's 1 to 2, okay? Non-isentropic. Non-isentropic compression. Okay, so process 1 to 2 is non-isentropic. 1 prime to 2 prime is isentropic. So in this case, 1 prime, 2 prime, 3 prime, 4 prime is the ideal cycle, and the actual cycle is 1, 2, 3, 4. What is the other difference? The other difference is the location of the ones. 1 prime moved from here to here. So that means it's not exactly on the dome. What is coming out of the evaporator increases in temperature. So the temperature is T evap only inside the dome, okay? T is constant only inside from here to here. But outside it increases, and this is the T superheat. It increases, and the point at 1, the temperature is basically TE plus T superheat. Okay, T1 is TE plus T superheat. So it's superheated vapor. It's all vapor. And then non-isentropic compression, you get to point 2. This compression includes losses due to friction and the speed of the compressor, which creates irreversibility, right? So non-isentropic compression, and then from 2 to 3, it doesn't stop at 3 prime. You cool the condenser and you reach fully liquid in the condenser here, and then you cool it a little bit more. So that change in temperature is T subcooled, okay? Delta T subcooled. You could say delta T. Same here, okay? So delta T subcooled from 3 prime to 3 prime, 3 prime to 3. And when you reach 3 with all the liquid, you expand through the expansion device. And 3 to 4 is again isentropic. And 4 to 1 is the evaporator heat transfer. So the difference in process 3 prime to 4 prime and 3 to 4 looks like this, right? 3 prime to 4 prime, the inlet also has a little bit of bubbles, and when it comes out, it's fully two-phase. In 3-4, there's no bubbles at all. It's fully liquid, and it's coming as two-phase. And the difference between 4 prime 1 prime and 4 to 1 looks like this, right? Um, in the first case, by the time it reaches 1 prime, there is still a little bit of liquid left. But in the second case, by the time it reaches 1, there is no liquid left and it's fully vaporized. Okay, so the superheating, subcooling, and non-isentropic compression are the main differences. Now, typically, how does this affect the performance? Typically, subcooling is good, okay? Increases COP, increases COP, increases the performance.
of this. So subcooling is a good thing. Superheating, sometimes good, sometimes bad. Um, could be good if you optimize the superheat, right? So this could also increase superheat. The main reason the actual VCRS is bad compared to ideal VCRS is because of the non-isentropic compression. So the non-isentropic compression makes it less efficient. So the overall efficiency for the actual VCR cycle is the same formula in this case, right? Because we have moved the points 1, 4, 2, and 3. So the formula is same now. The ideal VCRS cycle, the formula is different it's based on the 1 prime, right? So the efficiency of which one would be better? Typically, the ideal cycle would be better, and that's because of the difference in the isentropic versus non-isentropic compression. Um, the subcooling and superheating actually helps, um, especially subcooling.
Now let's look at the components of the lab experimental setup. Here we have the three views of the lab setup. Here we have the front view, this is the top view, and this is the back view. Um, and as we have discussed before, we have four major components: the compressor, evaporator, condenser, and the expansion device. Let's look at those first. But overall, there are 24 components shown here. So the heart of the system, the compressor, is basically here, and it's item number 12. So this is a sealed compressor, fully sealed. All the motor, oil, everything is inside. All the moving parts are inside, so it's fully sealed. That's why it's called a hermetic compressor. And then the compressor is connected to, um, the outlet of the compressor is connected to the condenser heat exchanger. So which is this number 11 here is the condenser. And then the evaporator is number 14, which is on the left. So the right side is condenser, this is condenser, this is the evaporator heat exchanger. As you can see, they both don't have any fans. There are no fans in the system. So we are cooling them using cooling water. So you can see a number 10, which is the condenser cooling water outlet. So you can see that under this tape here, you have both the condenser refrigerant tube and a water tube that are um, attached to each other as a heat exchange setup. Similarly, there is a water heating line for the evaporator, which exchanges heat with the evaporator refrigerant. The fourth device, the major device in the vapor compression system, is the um, expansion device. And the expansion device is located here, the same as this, right? It expands high pressure refrigerant to a low pressure refrigerant and feeds the evaporator. So it's number 17 in this list, the expansion valve. Evaporator we already looked at. So those are the four major ones. Then we have a lot of measurement devices, right? So we have flow meters for water. So you have a condenser water flow meter and a refrigerant evaporator water flow meter. We have two pressure sensors, one for high pressure, one for low pressure. Then we have a safety device for extreme pressure scenarios. If the pressures are not what are expected, so this device will turn off the system. Then we have a device where we can monitor the temperatures and the power on this LCD screen. Um, and then we have separate system for bringing in cooling water. So both the condenser and the evaporator are supplied using one line, one input line, and they're split here. One goes to the condenser and another goes to the evaporator. They go to the flow meter first before they go into the evaporator. And one of the major things to understand here is the refrigerant used is R134A. R134A is a hydrofluorocarbon refrigerant. Um, it's slowly being phased out, because of the high global warming potential. Um,
but it's still being used in Thailand. It's primarily in domestic refrigerators and also in automotive air conditioners. All right, so this is the schematic of the system. So if you look in here, um, it looks a little bit confusing, but all the blue lines are water lines, okay? So these are water lines. All the red lines are high pressure refrigerant lines, okay? And the purple ones are low pressure. So if you think that way, it'll be easier to understand. Low pressure refrigerant, okay? So if you look at the water supply line, it splits into two. One goes to the condenser flow meter, right, number 10, okay? And then it goes to the condenser heat exchanger and it comes out. If you look at the other water line, it goes to the evaporator flow meter, evaporator cooling water flow meter, and then goes to the evaporator heat exchanger, and then comes out. Okay. Um, if you look at the refrigerant, let's start from the compressor. Okay. This purple line is the inlet to the compressor. It's coming in, and it's going out through the red. So the red line is connected to the pressure sensor, but then it's also connected to the condenser. Okay, and it cools down and goes from the condenser all the way to the refrigerant flow meter here, okay, number 12. So condenser outlet goes to the refrigerant flow meter, and after that it goes to the expansion device. And after the expansion device, it goes to the evaporator. Okay, and once it goes to the evaporator, it exits and goes back to the compressor, the inlet. So that's the cycle. You can look at the color of the lines and you can see after the expansion device, the color is purple, so the pressure dropped, right? And then after the compressor, the purple changes to red, so the pressure increased. So the lines between uh, expansion device and the compressor, uh, that's where the line switches color, right? When it goes across the compressor or the expansion device, the pressure changes. So that's where the color changes to. Now, if you look at the measurement systems, um, so you already have two water flow meters, 10 and 11, and then you have a refrigerant flow meter, 12, two pressure sensors, one connected to the red line, which is high pressure, the other connected to the purple line, which is the low pressure. So this measures pressure in the evaporator, this measures pressure in the condenser. 9 measures pressure in the condenser, 8 measures pressure in the evaporator. Um, Temperatures. There are three temperature sensors for the water line. One is the inlet temperature of the water, which is same for both condenser and evaporator, and the outlet temperature, which is different for evaporator and condenser. The outlet temperature is T6 for condenser and T7 for evaporator. So the three temperatures for water, and then the remaining temperatures, 1, 2, 3, 4, are for the refrigerant lines, T1 to T4. T1 is at the inlet of the compressor. T2 is the outlet of the compressor. And T3 is at the outlet of the condenser. Okay. And the remaining one, T4, is right after the expansion device at the inlet of the evaporator. So those are the four temperatures that we'll measure. Okay. And that pretty much sums up all the measurement devices that you have to collect data for. 7 temperatures, 2 pressures, and 3 flow rates. Okay. All right. Now let's get into the test process. The first thing is the pre-test inspection. Um, Most of this is already done for you, so we have already made sure that the trainer is placed on a level surface because you're using a lot of rotometers, flow meters that needs to be leveled for good readings. Then you have to make sure the electrical cables and connectors are in good condition. There are no leaks on the water lines or the refrigerant lines, which is also done on a regular basis, which will also be done on a regular basis by in the lab. You have to make sure that the ELCB and the CB, the circuit breaker and the earth leakage circuit breakers, they're all they're all switched off before connecting the power. You have to also make sure that the power switch is switched off before you plug in the cable. Okay, so once all those are ready, you can plug in the cable. Um, you have to also make sure that the water hoses are directed to a safe drain and they will not flood the lab. All right.
So now let's start the experiment. So starting the setup, the first thing to do is to open the main water supply valve. So this is the supply valve that you have in the lab that would connect to um, number 23, which is the inlet, cooling water inlet, that supplies both the condenser and the evaporator heat exchanger. Once the main water supply valve is opened, you want to make sure that you're opening the valves on the two flow meters, one for the condenser and one for the evaporator. And in this case, you would be opening by rotating to the left or counterclockwise and closing by rotating to the right clockwise. So as you're rotating to the left, you can adjust the flow rates to the right level, required level for your test. But one thing to keep in mind is that the flow rate for the condenser side, condenser cooling, should not be greater than 6.4 liters per minute. And the evaporator flow rate should not be less than 3.2 liters per minute. So the condenser cooling water, it could be anything like 4 liters per minute, 5 liters per minute, 3.4 liters per minute, but not 6.5. Okay, it can go up to 6.4. The evaporator flow rate, on the other hand, could be anything above 3.2, 3.3, 3.4, but not 3.1 or 2.8 or something like that. So this is something very critical. Make sure that you have the required flow rate already going through both the heat exchangers, right, before we turn on the system. Now, turning on the system would mean you will first turn on the circuit breakers, right? The circuit breaker and the uh, earth leakage circuit breaker. So turn on both of them, then turn on the power switch. Okay. Now, after the system is started and the power switch is on, you will not notice the compressor turn on immediately. It will take some time. Typically, it takes about 5 to 7 minutes for the compressor to turn on. Okay, and you would easily recognize it because compressor is pretty audible. And when the compressor turns on, your clock starts. Okay, so time t equal to 0, we'll consider that the compressor turning on. Okay, and from t equal to 0, if you allow for at least 20 minutes for the first test data point, um, you would be closer to steady state or stable operation. Now, how do we make sure that it is steady state? You will be monitoring the temperature on the screen, right? There are 7 temperatures, and see whether they are getting stable. You will also be looking at the pressure sensors, the high and low, and then the 3 flow meters, 2 for water and the 1 for refrigerant, right? So you'll be monitoring all of these to make sure you're reaching steady state. You're primarily monitoring the temperatures, right? That's easy to see with the numbers changing. Others, you're looking at the scale. The problem with the water flow meter is it's connected to a lot of other supplies in the lab. So if somebody else or someone else is opening the tap and that creates a big enough pressure differential, then your flow rate through the water supply meters could also fluctuate. So you have to make sure they are not fluctuating and they are steady. And if they are fluctuating, you have to make sure uh, more than 20 minutes is passed, probably, to ensure all the other parameters are stable. Okay. Now, it takes longer for the first test point to reach steady state. Afterwards, typically it takes less, maybe roughly around 10 minutes.
So allow at least 10 minutes and monitor the temperatures and other parameters that I mentioned here to ensure that the steady state is reached. Now, what are the recommended test conditions? These are the recommended test conditions, and it is recommended that you run them in sequence. You can see that there are only two parameters that you can control: condenser cooling water flow rate and the evaporator cooling water flow rate. These are the only things you can change in the test. So basically, you will be only changing the location of these knobs, right, to get the right flow meters. The other thing to notice here is that it's not independent. When you change this, this value also will change a little bit. So you'll have to adjust this, the knob on both of them to get to the right test set point. So the first test, if you run 3.4 liters per minute in both of them, you should wait at least 20 minutes after the compressor turns on. And after you switch to another flow rate, for example, for evaporator, you switch to 3.8, then you wait another 10 minutes, right? So finish all the evaporator test points by changing the evaporator, but make sure you adjust the condenser to make it closer to 3.4 and then switch. Okay, we are not trying really higher flow rates primarily because usually there's less pressure in the lab to get higher than 5 to 6 liters per minute. You're welcome to try if you want to try other flow rates, but this is what is recommended. Okay, now what is the data that you have to collect? Of course, the two pressure sensors, right? And the 7 temperature values, the 3 flow rates, refrigerant flow rate, and the 2 water flow rates. In addition to that, you have to get the power data from the compressor, and that you can obtain from this dial here, right? This dial. So you can click on the watts option or the voltage and current option here. In this case, it's showing 642 watts, so that's the compressor power. Okay, so you can switch to voltage and current to get those numbers too. So this is the most important value. Okay, this is the most important data. Even if you got the current and voltage wrong, we are primarily using watts value for calculations. All right. And all these records has to be done at steady state. Um, so all of these values should be varying very minimally uh, when you're recording them. Okay, so once you finish all the test data points, the next step is shutting down the system. So the first thing to do is turn off the power switch, and you know where the power switch is. It's this one. And then you switch off the circuit breakers and the ELCB, right? Afterwards, you can disconnect the power supply cable. Once you did all of these, then you can close the water supply valve, the main water supply valve. And then you have to drain all the water from the system, wipe all surfaces dry. And the primary surface that will be wet is the evaporator. You could see after all the tests, there will be a lot of condensation forming on the evaporator coil. So we have to wipe them off, make them clean, right? And then inspect for any other leaks, water leaks, or any moisture buildup that you see anywhere else. So that's the shutdown procedure. So now some general safety warnings. Um, Never operate without sufficient water flow through both the heat exchangers. This has been already explained. Evaporator flow should always be more than 3.2 liters per minute. Condenser flow should be never more than 6.4 liters per minute. Then do not over twist the flow meter valves, which are the only things that you'll be operating within the system. So be careful to not over twist in either direction, right? Do not attempt to open any of the refrigerant lines. The compressor and the electrical parts of the compressor, mainly the capacitor, you should keep your hands clear of them to avoid the risk of potential electrical risk and also thermal risk. Compressor is typically more than 80 degrees C hot, so you could get minor burns if you touch it. Okay. If the pressure stat trips, which is the component that you've seen here, um, this component, if that trips, it's usually because it's detecting some unexpected pressure, maybe a really low side pressure or really high side pressure. If that happens, just notify the instructor or the lab technician or the teaching assistant, and they will identify the cause, whether it's overpressure, underpressure due to insufficient water flow, or is it a leakage of refrigerant or some other cause before the experiment is reset. Okay, now let's discuss some best practice, best practices involved in reading some of the measurement devices in our system. Start with the water volume flow meters or rotometers that we are using. Um, there are two such meters. Both of them have the same model number, same scale. Um, the scale on the right is in liters per minute, and that's what we will use. Scale on the left is gallons per minute. We are not going to use that. Um, for the right scale, it varies from 1 to 7 liters per minute. The scale starts at 1 and it ends at 7 liters per minute. The major division, if you look at the major division, is from 3 to 4, 5. So the major division is 1 liter per minute. The minor division, you have 5 divisions in between, right? 1, 2, 3, 4, 5. So each of them is zero point 0.2 liters per minute. Okay. Now the float, this float is inside a variable area um, tube. So you can see the area inside the tube is varying. So the float will balance wherever the velocity um, matches the weight of the float, right? So depending on the flow rate, the velocity that matches that float's height will be at a different height. And the float will be slowly rotating. That's why the name rotometer. Now, where should we look at to find the flow rate? You should look at the top surface of the float. Okay, top surface of the float is where you should measure the reading, and on the right side scale. Now, when you take the readings, you should keep your eyes parallel to the float and don't look at it from an angle like this or an angle like this. Try to look at as straight as possible to the top edge of the float. Otherwise, you could get the wrong reading, right? And avoid taking picture because the camera angle usually would give you the wrong reading. You should only take the readings based on naked eye, and the eye should be at parallel to the top surface. Whenever you have a reading somewhere in between, try to do your best interpolation between those two. Try to divide as percentages inside. So in this case, let's say this is roughly 45% of the gap here, and use that 45% of 0.2 liters per minute to find that value, right? Now adjust the flow rates. In this case, actually, you're not um, gonna put some value somewhere in middle. If you're testing based on the recommendation here, you'll always be placing it on a mark that's already in here, right? So in that case, try to adjust the flow rates using the knobs to get the right location for the top surface for both the condenser side and the evaporator side. So that's about reading the water volume flow meter. What about the pressure gauges? The two pressure gauges, the low and high pressure gauge, their readings ranges are different. Okay, so the low pressure gauge, it has two scales. It has an outer scale. You can see numbers 0, 1, 2, 3 on the outer scale, and then you can see 0, 20, 40, 60, 100 on the inner scale. You should use the inner scale, which is measuring in psi. I have written psi-G here, which means it's gauge pressure. Okay, gauge pressure. It's different from absolute pressure. Um, Absolute pressure is the actual pressure of that particular measurement. Gauge pressure is neglecting the atmospheric pressure. So you have to add the atmospheric pressure on top of the gauge pressure to get the actual total pressure. Okay. So first of all, let's look at the scale. If you look at the PSI scale, each large division, okay, so if this is 40, then this is 50, and this is 60. So each large division is 10 psig. The major division is 10 psig. And there are 5 divisions in between, so each of those 5 division is 2 psig. Okay, so if you have any value in between, you have to do the best interpolation. So if it's somewhere here, you can say, oh, that's 50% between them, so it's 50% of 2 psig. So that is 1 psi over the previous reading. So do your best approximation of that interpolation to measure the um, pressure values. And this is really critical. A small change in this pressure creates a big impact on your evap temperature calculation. Okay, so be really careful. Now, the measured pressure, let's say if it's 50, the actual pressure would be by adding the atmospheric pressure to that 50 value. So 64.7 psi would be the actual pressure. Just like the flow meters, you should look at um, the gauge with at eye level without using any cameras, and that's how you should read the gauge. All right, now let's look at the high pressure gauge. It's almost the same model, but the range and the scales are different. Okay, in this case, the PSIG scale is up to 0 to 500 because it's in the higher pressure range, right? It's measuring the condenser pressure, which is a little bit higher. The major division, you can see from 100, and this is 150, so this is 125. So the major division is 25, and it has 5 divisions inside, so each of those 5 divisions is 5 psig. Okay, so just like before, you make sure you're doing the interpolation correctly when your value is somewhere in between the minor divisions. If the gauge pressure is 145, then the actual pressure would be again just adding the atmospheric pressure. Okay, and same instructions about measuring at eye level. Now, reading the refrigerant volume flow meter. This is similar to the water volume flow meter. You have to look at the top surface, right? Majority of the time, your reading will be between um, these two marks, right? Unlike the water flow meter, this is not something you control. This is something that just happens based on all the water temperature and everything, okay? And usually it is uh, varying between these 2 points. Now, let's look at the scale. It measures in liters per minute from 0.25 to 1.4. That's the range. The major division, you can see it's 0.4, 0.6, so the major division is 0.2. And the minor division, it has 1, 2, 3, 4 divisions in between. So each of them is 0.05 liters per minute. Okay. Like I said, most of the time you'll be, so this one is 0.55, right? So most of the time you will be measuring between 0.55 and 0.6. So you have to be really careful by looking at eye level and figuring out, okay, is it 10% above 0.55 or is it 100%? So figure out a percentage and then use that to estimate what is the flow through the system. And it'll be infinitesimally small for the different tests you do. So it's very critical you pay a lot of attention here. The other thing to notice here is that you have to ensure steady state, right? There are no bubbles going through this system because at some points um, you may notice some bubbles going through here. This is a volume flow meter, not a mass flow meter. So if there's both a liquid and air is going, sorry, both liquid and vapor is going through the rotometer, then the reading that you're taking is wrong. So it should only have single phase going through it to make sure the volume flow rate is correct, and it should not have any pulsation. We can look at what that means by looking at this slide. So on the left, you have bubbles. Okay, if you look carefully, you can see the bubbles. On the right, there is no bubbles in the flow meter. So this is how it should be when you're doing the measurements. You can also check the sight glass, which is before the flow meter, and look for whether there are bubbles there too. So if you see bubbles here and you don't see bubbles in this, even then you shouldn't take readings. You should see no bubbles here and no bubbles here when you take the readings. Okay. It is usually occurring during the initial startup, um, and it should stabilize after 5 to 10 minutes. The bubbles should disappear, but it's possible it can appear back at other test points depending on the water temperature and flow rate. Let's look at some videos to understand what is wrong and what is right. So this is an example of um, the flow in the flow meter and the sight glass having bubbles, right? And this is an example of the correct flow. In this case, there are no bubbles in either of them. All right. Now, once you finish the test, there are 4 different activities to be completed afterwards. First is a question answer session. Second is you have an activity to draw the location of various components on the test system on a pH diagram. Third is, of course, the detailed data analysis, which will include all these bulleted items. Heat transfer in the condenser and the evaporator by calculating both the refrigerant and water side energy, compression work, actual isentropic and electrical compression work, compression efficiencies, coefficients of performance, evaporator temperature effect on coefficient of performance, condenser temperature effect on coefficient of performance. Then you should do the report writing, and the report should include whatever you found for items 2 and 3 from above. All right. Activity 1 is basically the instructor will be asking you some questions after the end of the experiments to test your understanding of the experiment. Activity number 2 is basically you can pick a pH diagram, right, with the vapor compression cycle that looks something like this. Then you have to mark the location of these components that are in your setup, in the lab setup, where they are located on this pH diagram, right? Okay. And activity 3 is data analysis. In this activity, you could use the lab laptop that will be provided and use the Excel file that also will be provided for calculating some of the performance numbers that are needed to understand the vapor compression cycle. If you're using your own laptop or PC, you can install the CoolProp add-in for Excel. Separate instruction and installation files will be provided. The lab laptop already have this installed, right? CoolProp formula for calculating the following parameters are already provided in the Excel. So if you look at the Excel file, right, and this is the experimental data from your data sheet, right, the first few columns. So all of these are measured in the lab, and I'm showing only one test. So based on those measurements, this Excel file will already do some basic calculations for you. It'll calculate the evap pressures, it'll calculate the evaporator temperatures, it'll calculate the superheat, subcooling, and it'll use the CoolProp. Let me zoom in here. It'll use the CoolProp formulas. You can see the formula here, props SI formulas for calculating a lot of these refrigerant properties, right? and up to column AF, it will be calculating all the required properties for you. Afterwards is the place where you would be doing the calculations. And the formulas are already given here, right? So you'll be calculating heat and work calculations, rate of heat transfer, isentropic compression, actual power, all of that in here. So that would be part of your activity, right? Calculating the additional parameters. Then once you finish all those calculations for all your test points, then you should plot the COP of system versus TE. And we'll look at what COP of system is later on um, in the next few slides, right? You'll plot the COP of the system versus the evaporator temperature at constant condenser temperature. And then you'll note down your observation. How is it varying, right? What kind of variation is that? Do the same thing with condenser temperature at constant evap temperature. And again, you'll provide your observations, right? Okay.
Now let's look at how most of these values are evaluated in the Excel based on the measured values. So let's start with the pressures that are calculated here. Okay. So estimating the evaporator and condenser pressures, it's based on the two pressure gauges that you have in the system. One measures the low pressure and one measures the high pressures. The low pressure is basically represents the evaporator pressure, and the high pressure represents the condenser pressure. As you're already aware, the gauges measure the pressure in gauge pressure in PSIs. So we have to convert that to absolute pressure in pascals. So first thing we do is you add 14.7 psi to convert it to absolute pressure and then convert psi to pascals using the Excel convert formula. You could use other methods of converting. You could look up online and use a factor to multiply, but this is one of the easiest way to do this. Okay, so once you have the pressures converted to pascals, now you're ready to use CoolProp to actually find the evap temperatures and condenser temperature. So how do we estimate those temperatures? So let's take the case of condenser temperature. In this case, condenser temperature is constant only along this orange line where it's inside the two-phase system, right? So wherever it's inside the the two-phase envelope, it's constant temperature, it's condensing temperature. But we don't have a sensor to measure that. What we measure is actually T3, which is located at this point. It's outside the dome. It's in the subcooled region. It's fully liquid. So T3 is not the same as TC. T3 is a little bit colder than TC. So how do we estimate TC then? We estimate TC based on the condenser pressure, which is same as the pH, right? So how is it related? TC is basically the saturation temperature corresponding to a pressure PC for the refrigerant that we are using, which is R134A, right? So for each type of refrigerant, there will be a one-to-one correspondence between the saturation temperature and the saturation pressure. So once you find TC, the difference between TC and T3 is how much you have subcooled the refrigerant. So that delta TSC represents the amount of subcooling, TC minus T3. Okay, all right. Now the same thing for evaporator. The evaporator temperature is represented by this blue line, right? Um, Along this line, the evap temperature is constant. Just outside the dome, it starts getting heated a little bit more, right? It gets superheated. So in this case, the TE is again measured based on the pressure in the evaporator, which is PE, and it's the saturation pressure
one-to-one correspondence between temperature and pressure. So you use the thermodynamic properties to find out the TE once you know the pressure. And the difference between uh, the TE and T1 is ideally the superheat. But in this case, because of the measurement errors, we are planning to use T1 minus T4 as the amount of superheating. Okay, so we have a thermocouple that is measuring T1 and we have a thermocouple that's measuring T4. So the difference between them is what we will use as um, the superheat value. So the reason for that is ideally, uh, if no measurement errors, we could use evap temperatures as the same as T4. But this is not true. This is not true. Okay. So you will see that if you convert pressure, you'll get a temperature that is a little bit higher than T4, or sorry, a little bit lower than T4. So we'll use the TE that is predicted by pressure rather than the one predicted by temperature. However, the delta temperature probably it will be more accurate if we use between T1 and T4. So keep that in mind when you do the calculations, okay? So this will minimize the errors in your calculation if you do it this way. So superheating delta is between T1 and T4. The actual evap temperature is a function of PE, so it is calculated separately, not using T4. Okay, so how do we do this using Excel? In this case, you have to start using the coolprop formula. So you have two pressures, right? And you have corresponding two temperatures. How are we doing that? If you look at the formula in each cell, you'll see it's calling a props SI function, which is a coolprop function, and it's trying to output a temperature. Okay, this is the output it's looking for. And it's giving an input of pressure, and typically the pressure units is Pascal. So it's already looking for a Pascal value. D4, in this case, D4 is here, D4 pascals, right? And then Q is quality. Basically, if you input Q, it already means that you are on the dome. Okay, if you have a pH diagram, right? If you are inputting Q, that means you're on this dome. And Q is equal to 1 means you're on the quality 1 on the dome. So it's in the vapor, almost close to vapor phase. And that basically gives you the saturated temperature as output. And the C star 2, it is trying to call the refrigerant name. Okay. This is converting the Kelvin value to degree C. So finally, this is the uh, T evap for that particular pressure. Similarly, the condenser pressure is used to calculate the condenser temperature. Okay, very similar formula. All right, so that's how we estimate the evaporator and condenser temperatures using coolprop.
Now let's look at estimating the temperature and enthalpy at state 1. So the temperature, ideally, you would think that, oh, we are measuring T1. So T1 is the inlet temperature to the compressor. So that's what the value we should be using. Um, However, we shouldn't use this value directly as the inlet temperature to the compressor. Instead, we should use the um, value that is the calculated value for T1, which is TE plus delta TSH. For the same reason that we had mentioned before. The reason is there is some measurement error when you measure temperatures on the evaporator. So we have to go back to the temperature estimated using the pressure, which is the evap temperature value, TE, and then find that delta temperature between T1 and T4 and use that as the superheat value, delta TSH, and then add that to the estimated TE, right? And this will be your new T1. instead of using the measured T1. Okay, so once you get that the estimated T1, the next thing you need is a pressure to estimate the enthalpy. And the pressure would be basically the evaporator pressure. So once you have the evap pressure and the estimated T1, which is this, you can use CoolProp or other thermodynamic tables to calculate H1. Okay, let's look at how it's done. So let's take this case where we have the evap pressure, evap temperature, and delta TSH, right? So use these two, um, the TE and delta TSH, to create the estimated to calculate the estimated T1, right? Which will be this C3 plus D3 plus 273.15, which converts that to Kelvin. So that's the value for T, and the value for P is the evap pressure in pascals. And then you put in the name of the refrigerant, which is A star 1. You will get an output based on the output parameter you put here, which is H, and that stands for enthalpy, and you'll get an enthalpy in joules per kilogram. Okay, that's the unit that CoolProp will estimate this. Um, so now we know everything about the inlet of the compressor. Okay, we know the enthalpy, we know the pressure, we know the temperature at the inlet. Now what happens at the outlet? Um, for the outlet temperature, we will use the measured temperature T2. Okay, and in this case, the pressure at the outlet is same as the condenser pressure. So we have a temperature and we have a pressure. We can easily calculate the enthalpy because it's again in a single phase region. So it'll be used, we'll be using the CoolProp to estimate that in the following way. So suppose you have the pressure of the condenser and temperature at the outlet of the compressor. Use the formula like this, temperature and pressure. Convert the temperature to Kelvin, and you will get the enthalpy at state 2. Okay, notice that the enthalpy at state 2 is going to be higher than the enthalpy at state 1. Okay, this is 41,000, 414,000, and the other one is 460,000. Okay, all right, so now we know states 1 and 2. We need to know about state 3. Enthalpy at state 3 is estimated based on temperature at state 3 and the pressure at state 3. The pressure is the same as at state 2, which is the condenser pressure. And the temperature T3 is the measured temperature T3 measured by the lab uh, temperature sensor. So the calculation looks something like this. The estimated compressor pressure, condenser pressure, and the condenser outlet temperature will be used to estimate H3, again in joules per kilogram. So that's state 3. Now we need to know state 4. State 4, H3 and H4 are same because it's an isenthalpic line, right? So since H3 is H4, we already know the value of H4. Okay, and what about the pressure? The pressure here is same as PE. Okay, PL and is same as P evaporator. So we know the pressure. Okay, and the temperature here would be same as T evap. Okay, so at 4, the temperature is T evap, pressure is P evap, and enthalpy is H3 equals H4. Okay, so we know um, the three main parameters that we need to calculate the rest of the thermodynamic properties. Okay. So far we have calculated the enthalpies and other properties for the actual state points of the cycle, including at 1, 2, 3, and 4. What about an ideal cycle and the ideal compression process, which is basically an isentropic compression process? Instead of 1, 2, it will follow the path of 1, 2s, where the entropy is constant. So at 1, we know the enthalpy, temperature, and pressure, right? At 2s, we don't know the enthalpy, we don't know the temperature, but we do know the pressure. That pressure is same as the condenser pressure, right? Well, how do we determine the enthalpy at 2s? We need at least two properties to determine that. Well, thankfully, we know that this is a isentropic line, so the entropy at 1, S1, should be same as the entropy at 2s. So S1 should be same as S2s. So if we can find S1, we'll know S2s and we'll have two properties at 2s. And using those two properties, we can calculate the enthalpy at 2s. And the reason we need at least two properties is because it's a single phase. You'll need only two properties. So in this case, S1 is first determined. We haven't estimated S1 so far. So S1 is first estimated using the two properties we already know at state 1. One is the temperature, which is TE plus the delta superheat, which is the actual T1, not the measured T1, and the pressure. So using those two, you can use CoolProp to calculate this or other thermodynamic tables, calculate S1, and now once you get S2S, the enthalpy at 2s is basically a function of entropy and the condensing pressure, which is the pressure there. All right, so let's use the thermodynamic tables to calculate, basically the CoolProp to calculate this. So in our case, S1 is first estimated here using TE, delta DSH, and PE. Okay, and this is the formula. So D3 is basically TE, the E3 is basically delta DSH, and we convert that into kelvins, and the pressure is basically P3, which is the evap pressure for refrigerant R134A. And you get the S1 value, which will be in joules per kilogram per Kelvin. Okay, and the enthalpy at 2s, which is H2S, is calculated using S2S. Now S2S is same as S1, so equal to F3, right? So the formula for S2S is just equal to F3, which is same as this. Now, how do we calculate the enthalpy at 2S? So you use one variable as S, which is the enthalpy at F3. You could use G3 too, okay? So this actually should be G3, but you'll get the same answer because they have the same entropy. And the pressure, which is the condensing pressure, which is in C3. And if you use those two and the output is H, you get the enthalpy at 2s. So that would be this point here. So you'll know the enthalpy at 2s, H2s there, right? Okay. Now let's look at estimating the refrigerant mass flow rate based on the volume flow rate that we measure using the rotometer. So what do we need to convert the volume flow rate to the mass flow rate? We need the density of the refrigerant. And the density of the refrigerant should be measured close to the flow meter. Ideally, the density should be the density that's entering the flow meter. So we don't have a density measurement at that point. So how do we estimate the density? If you look at the uh, schematic of the experiment, you'll see that the closest temperature measurement before the flow meter is the temperature at T3, okay? And that is basically the temperature coming outside of the condenser, okay? Condenser outlet. So we'll use that as the inlet temperature for the flow meter. And what is the pressure? You can see that the pressure going to the flow meter is the red line, which is the high pressure, which is same as the condenser pressure, PC. So we know the T3 and we know the PC, we can figure out density, okay? Density is a thermodynamic property. Just need two properties to figure out the third thermodynamic property, provided that
the refrigerant is in liquid state, right, or a single phase state. If it is in two phase, then we cannot use just two properties, right? We also need to know the mixture of refrigerant in gas and liquid to figure out the individual densities of the gas and vapor, gas and liquid in there. But we do want to make sure that this is in liquid phase, which is why we make sure there are no bubbles in the flow meter and there are no bubbles in the site glass, which is number 5. So if there are no bubbles here and the flow is in steady state and we have taken the reading at steady state, then we could use the temperature here and the condensing pressure to calculate the density going into the flow meter. Once we get the flow meters, the density going in there and the volumetric flow rate of the flow meter, you multiply those two to get the mass flow rate in kilogram per second. Okay, let's see how to do this in CoolProp. So um, in this case, the measured flow rate is in liters per minute. It is first converted to meter cube um, per second using this formula here, right? So this converts into meter cube per second. Um, so multiplying D3 to this is meter cube per second. Okay, converting the liter per minute to meter cube per second. Now multiplying E3 to that, density to that will give you the kilogram per second. And how do we calculate density? We use the temperature at B3, which is nothing but temperature T3, and add 273.15 to convert it into Kelvin, right? And the condenser pressure, which is PC, it's in C3, okay? So use that formula, you'll get a density of close to somewhere around 1000, about 1000 um, kilogram per meter cube, and you'll get a flow rate somewhere close to 0.012 kilogram per second. Okay, so that's how you estimate the refrigerant mass flow rate. And the reason we need refrigerant mass flow rate is you can see most of the values that we estimated here are in joules per kilogram, right? So we need to convert, if we need to convert the work done into watts, you need to multiply that with mass flow rate. If you need to convert the cooling rate in joules per kilogram to watts, we need to convert that to, we need to multiply that with the mass flow rate of the refrigerant. Okay, all right. Now estimating the actual heat transfer at the refrigerant side. So basically, if you are looking only at the refrigerant, how much is the heat gained by the refrigerant from 4 to 1, right? From 4 to 1, how much is the heat gained by the refrigerant from the water, right? So that'll be basically change in enthalpy from between 1 and 4. So H4, sorry, it should be H1 minus H4, okay? And the evaporator heat transfer rate would be multiplying this joules per kilogram with kilogram per second of refrigerant flow rate. So multiplying the mass flow rate with H1 minus H4 will give you the watts, cooling watts. So this is basically, so when you look at buying some refrigerator or air conditioner, they will rate a capacity in certain tonnage. They are basically talking about the cooling capacity, which is nothing but this value, right? This is what the cooling capacity they are talking about. The amount of heat that the evaporator can remove is the cooling capacity. You can term it as Q dot E, QL, or QE, depending on what units you're using. All right, now on the condenser side, we will transfer a lot more heat than on the evaporator side. And this heat is basically a difference in enthalpy at 2 and 3. Okay, so this is the condenser side, and the difference in the enthalpy at 2 and 3 will give you the total heat that is rejected from your system. And converting that to watts, you just multiply with mass flow rate, just like before. All right. Now, the third thing we need to know is the compressor work, which happens between 1 and 2, right? So if we start with the ideal scenario, the process is 1 and 2s. In this case, the work done is the enthalpy difference between 1 and 2s, right? So whatever the enthalpy at 2s is and at 1, that difference. So that's in joules per kilogram, multiply with mass flow rate to get the isentropic compression power in watts. Now the actual thermodynamic cycle is determined, described by this notation W dot CA, would be calculating the enthalpy between 1 and 2. Okay, so you have already calculated H2 and H1. Now you use that to calculate the work done, W dot CA, okay, the actual thermodynamic work. Multiply it with mass flow rate to convert into watts. Now you're also measuring a power using a watt meter. Now that's the real, so both these things, these are work that directly seen on the refrigerant side, right? So if you're measuring refrigerant properties to calculate this work. Now, if you're not directly measuring refrigerant property, you're measuring the electrical power consumed by the compressor, you get the overall electric work, right? Now, what's the difference between these three works? The isentropic compression work will be typically the lowest. Okay, it'll be the lowest, and the actual work will be a little bit more, and the real electric power will be a little bit more than that. So what this means is in isentropic compression, there is no losses, right? No losses due to friction, irreversibilities, or anything. So most of the energy is converted to the fluid, directly transferred to the fluid. In actual compression process, there are some losses due to friction. There are losses due to heat transfer, right? And there are losses due to other irreversibilities, for example, the speed of compression, right? So there are more losses, so you need to provide more work to take it to the same condensing pressure, right? Now, in electrical work, in addition to these two losses, these three losses, there is leakage of refrigerant, re-expansion due to volumetric efficiencies, and losses in the electrical motor. Electrical motor will heat up, right? And fluid friction is also there, right? Fluid friction, oil, all that. So this includes all the losses. Okay, this is the real power that we have to give it to the refrigerant. The others are theoretical best power. If there is no motor losses, no leakage, then the W dot electrical will be almost same as the actual compression work. However, it's almost impossible to get to the isentropic compression because you can never have complete irreversibility when you compress the fluid because you will have to have a finite speed in the compressor. You cannot compress it infinitesimally slowly. All right, so based on these compression works that we determine, we can estimate a compressor efficiency. There are two types of compressor efficiencies that we are interested in. One is the isentropic compression efficiency, and that's defined based on this. So if you have isentropic compression work in the numerator and the actual compression work in the denominator, that gives you the isentropic compression efficiency. Okay, the formula is given here. The overall compression efficiency is you divide the isentropic efficiency with the electrical compressor power. Okay, so this includes all losses, and this efficiency, the isentropic efficiency, will be typically higher than the overall compression efficiency, which is the wire to refrigerant efficiency. All right.
Now let's look at estimating heat transfer on the water side for both the condenser heat exchanger and the evaporator heat exchanger. So the total heat transfer rate in the condenser side measured on the in the condenser heat exchanger measured on the water side is a very simple formula. It's MCP delta T, right? The mass flow rate times the specific heat times the delta T. This gives you basically the difference in energy that the fluid has at the inlet versus the outlet. And that difference is the heat transferred from the refrigerant on the condenser side. Now, we don't have a mass flow meter. What we have is a volume flow meter, the rotometer. So we do need to convert the volume flow meter measurement to a mass flow. How do we do that? We multiply it with density. And then we do need to estimate density and CP of the water. The other measurements, the volume flow rate and the two temperatures, inlet and outlet, are already available. So how do we estimate these two? One thing to remember here is both of these are functions of temperature. They're actually functions of temperature and pressure, but the variation with pressure is minimal. Okay, so they're primarily considered a function of temperature. However, for cool prop calculations, we will need to provide a pressure too, and that pressure will be the atmospheric pressure. The temperature for CPC is the average water temperature. So as the water is going through the heat exchanger, its temperature is changing, so the CP is not constant, right? So you have to take an average CP, and you will take that at an average temperature, okay? CPC at T average. Now, for density, you will not be using that T average. Density is uh, supposed to be measured at the inlet of the flow meter because we want to know the mass flow through the flow meter. We know the volume flow rate, we need the mass flow, right? So what is the density here that corresponds to that volume flow rate? That density will be corresponding to a temperature at the inlet, T5, right? So we will calculate the density of water at T5. This is true for both flow meter, both for condenser and for the evaporator, right? Because they have the same inlet volume water flow. Now let's calculate the condenser heat transfer using um, cool prop. So the two thermodynamic properties that we need are the density and the specific heat for calculating the overall heat transfer. So density is calculated using two properties, which are pressure and temperature. Even though the density of water is primarily only dependent on temperature, the variation due to pressure is very minimal. Cool prop needs both these properties to estimate the density, right? So for calculation purposes, we use atmospheric pressure, which is 101325 Pascal, for calculating both the specific heat and the density. So for density, the temperature is basically the inlet temperature. So if you look at the formula for density, you have D here, which outputs the density value, and temperature is A4, which is the cooling water inlet, right, in A4, and converted into pascals, and then, sorry, converted into kelvins, and then pressure of 101325 pascals for water. Okay, so this is for water. And the CP is for an average temperature C4, which is the average between T5 and T6, right? So the temperature is the average temperature and pressure is the same, right? And the output parameter is CP mass. So that way we get these two properties. And once you have that, what we need is the um, total energy in watts, or the total power in watts of heat transfer. So that is basically you're converting the um, mass flow rate into, sorry, volume flow rate into mass flow rate using this formula,
and multiplying it with Cp and the delta T temperature, which is here. So it's done in here. Okay. So this is basically this is basically converting liter per minute to meter cube per second. Okay. So the answer finally will be in watts. All right. So that's how we calculate the condenser heat transfer on the water side. For the evaporator heat transfer, the equations look very similar, except for the fact that now we have to calculate the Cp, and the volume flow rate um, is based on another sensor or another flow meter, and the Cp is based on temperatures T5 and T7. Okay, so main difference is the volume flow rate and the operating temperatures, but the formula looks very similar. Okay, so the Cp is estimated for this average temperature instead of T6, T5, and T7, and the density is estimated again at the same temperature T5. So use CoolProp in a similar way and do these calculations. Now, estimating the coefficient of performance, final performance of the system, right? There are different coefficients of performance depending on what you choose to be at the input and output. So in all these cases, all these three cases, our input is Q dot E, okay? Sorry, our output is Q dot E, which is the heat transfer on the refrigerant side, okay? The heat transfer on the refrigerant side at the evaporator. Now, the input changes. In the first case, the input is the isentropic compression. So if you take a ratio of cooling rate on the refrigerant side on the evaporator and take the ratio with isentropic compression, you'll get this efficiency. Okay, we'll call it COP, vapor compression system isentropic. This will give you the best efficiency or the highest efficiency. Now, use the actual cycle and use the actual compressor power, um, not the electrical power, the actual thermodynamic power, then you will get the actual COP VCRS cycle. So this will be a little bit smaller than the isentropic. Not a little bit, quite a bit smaller because of the difference in compression process. Now change the denominator again to the actual measured electric power. You get the COP VCRS overall. So this will be even lower COP. So all of these are based on measurements on the refrigerant side and the electrical power. Okay. Now, what if we completely avoid the refrigerant and only look at the water side of the heat exchangers? So only look at the cooling water heat transfer that we calculated in the previous slide, right? So only look at this um, heat transfer for the water side, and then only look at the electrical power. So we are not looking at any measurements or any thermodynamic property, just what we can measure in reality. Okay. In reality, you want, in this case, you are trying to cool water, right? So what is the change in water temperature and what is the energy um, transferred or removed from the water per second in watts, right? And what is the energy we had to supply, which is in the compressor. So that ratio is the actual system, overall system efficiency, right? So we will call it the COP system. That's the real efficiency. So there will be these four efficiencies that you have to calculate, okay? So once you calculate this, calculate the final system efficiency, which is the real efficiency versus temperature, and also versus two temperatures, the evap temperature and the condenser temperature. So in the first case, when you try to plot with the evap temperature, you have to make sure condenser temperatures are more or less constant. When you try to plot with condenser temperature, make sure the evap temperature is more or less constant. Okay. Um, in this case, what we are saying COP system is basically Q dot E water divided by W dot elect, which is the electrical power. Now, how do you make sure you get constant values of temperatures while one other temperature is varying, right? How do you keep T changing while TC constant? If you follow the test points that was asked in this video, um, the chances are you'll get something similar to this. Okay, so in this case, let's say this is the um, 6 temperature points that you got in your 6 tests. Okay, so if you look at the yellow points here, all the condenser temperatures are roughly close together. So you could assume that, okay, this is almost constant TC, right? TC is almost constant. So I can plot this T evap versus COP. Okay, so I can plot these evap temperature values with COP and say that it's at constant um, condenser temperature. The same way, if you look at this value, this value, this value, and this value, that looks like TE is constant, roughly constant. Okay, because there's a bigger variation when you go to 14.28. So you plot these condenser pressures versus COP to get TC versus COP plots. And the plot should be like this, right? The COP should be on the y-axis and the temperature, either TC or TE, should be on the x-axis. And you have to look at the trend. What happens to COP when the condenser temperature increases or decreases, and when the evap temperature increases or decreases, and why does that happen? You have to do some explanation there. Okay, so that concludes this lecture video. If you have more questions, you can ask in person in the lab with the instructor, or go through the document in more detail. All right, thank you.